Thank you very much. It's a pleasure to be here at Wigan to talk to you about astrophotography. This is something I've always been interested in. Astronomy has been a hobby of mine for a long, long time. It's nothing to do with the research I do at the university. Well, it's a little bit to do with the research I do because my research has always involved imaging of one kind or another, but normally that imaging has been associated with microscopes. I do imaging of atoms or imaging of molecules, or at the moment I'm interested in medical imaging and cancer diagnosis.
But back for a talk on that then.
So my interests have always been to some extent in photography, and that sort of overlaps with my interest in research at the university, but astronomy goes back even further. I've been interested in astronomy since I was knee-high. So astrophotography, where you can overlap interest in photography with interest in astronomy, that's why I've always had an interest in this subject. And what I'm going to do is spend maybe about half an hour giving you some background and talking about expensive equipment before I talk about photography without expensive equipment, and then we'll have a short break, and then we'll come back whatever it is, 20 minutes later, and I'll show you some more of my images. So that's how we're going to try and do things this evening. So I'll be starting with just what you can do with essentially nothing. I'm assuming that if I'm talking to a photographic society, I'm assuming you probably all own a camera. That's the starting point. So what can you do with just a camera and maybe just a tripod? Then we'll move on and say, if you did have an interest in astronomy and wanted to buy telescopes, then how might you do astrophotography with a telescope? And then having said that's really expensive, I'll then back off and say, well, what can you do with a star tracker? I'll explain what a star tracker is and explain that you can do a lot of astrophotography even if you're not interested in buying a telescope and using that with your camera to take pictures of very distant objects. We'll have a break before we return, where I'll show you a photo gallery of some of the images I've taken with the star tracker, which I hope will convince you you don't have to outlay a huge amount of money if you're interested in taking a picture of objects which are at, in some cases, enormous distances from us. And I'll finish with a little recap of what it's like to go to Africa when you can get really dark skies and take really nice photographs. So that's what I'm going to be doing. So we'll start simple. What if you just have a camera and a tripod, but you're interested in photographing the night sky? Well, this is what I did quite a few years ago. The story starts way before I went digital. I've been digital for, 20-odd years or so. This predates that, when I used to have a camera and enjoyed putting slide film in and taking pictures. So on a visit to Egypt to look at the pyramids, I hopped over the border, spent a night with the Bedouins under nice dark skies in Jordan. And if you simply put a camera on a tripod and point it north and expose for, in this case, looks like about 5 minutes or so, I'll try wherever possible to always show the camera and the lens and the exposure at the bottom here. This is what you would get if you pointed it towards the North Pole and exposed for about 5 minutes. What you see is evidence that the Earth rotates. No surprise perhaps, but it's rather critical to taking astrophotography, is you have to remember, even if it's on a nice stable tripod, the camera isn't stationary. The camera might be stationary relative to the Earth, but the Earth turns. Therefore, when you look up into the sky, it looks like the stars are wheeling in the opposite direction. So the entire northern sky seems to rotate anti-clockwise. One star doesn't seem to move much at all. That's Polaris, the North Star. It's not actually at the North Pole. It's not pointed to exactly by the Earth's axis. It's slightly off, but it hasn't moved much compared to all the other stars. You see, the further away you are from the North Pole, the more the stars have streaked. The Earth has turned, well, it was 5 minutes, whatever fraction 5 minutes is of a day. That tells you the amount that the Earth has turned, and so you can see the effect. It's a rather pleasing effect in itself. Of course, you can't expect to see an awful lot of detail because all the stars have blurred, or at least tracked, to produce these star trails. If you want to get the stars to be points of light, then you can't just keep the camera static. You have to move the camera, and we'll come to that in due course. But you're not limited to just taking a 5-minute exposure, as I did here with the slide film. With modern digital cameras, it's relatively easy not to take necessarily one very long exposure, but it's relatively easy to take a whole sequence of short exposures and then add them up together. You can add them up. How do you add them up? There's plenty of software that will do this for you. I happen to be interested in image analysis and image processing because that's my research, so I wrote the software to do that, but you can simply obtain free software to add frames together. And so with digital photography, you're not limited to 5 minutes. You can do a lot more, for instance, in this case, 6 hours. You can tell it's 6 hours because each of the stars has moved roughly 1/4 of a rotation, so that's 1/4 of a day. You also notice that Polaris is also not static. It might look static in 5 minutes, but after 6 hours, even it has moved a little bit. So this was taken from an observatory on the top of the mountain, the top of the volcano of Tenerife, because we take our physics students there. Once a year, we take our physics students, our astrophysics students, to the tiny observatory at Tenerife, and that's what you're looking at here. It almost looks like daylight because the domes look white and the grass looks roughly green or brown, but that's only because it was taken under moonlight. And when you take pictures under moonlight, then everything seems to come out a little bit like daylight. So the sky doesn't look black, even though generally speaking the sky is quite dark. It looks more blue simply because of the full moon. But because this was not one 6-hour exposure, it was actually 361-minute exposures. As well as adding them all together to produce star trails, you can, if you wish, put them together as a movie, and then you actually watch the Earth turn as the stars slowly rotate around Polaris. And again, there's software that will do this for you. There's free software such that if you take a whole load of individual images, the software will put them together either as a composite image or generate a movie for you. So you don't have to worry about how you do this. Free software will do it for you. But it gives a nice effect, and it's nice to be reminded that the Earth turns. We all know that. Galileo figured it out a long time ago. The Greeks figured it out a long time ago. You can either say the Earth is static and the sky spins, or you say the sky is static and the Earth turns. But it's nice to get this sort of video where you can see the stars wheeling around the North Pole. Occasionally, you might get a visitor. So, for instance, the solar system occasionally has comets coming through. This particular comet doesn't seem to have a very long tail, but it did suddenly get very large. It was a very compact comet. Then, in the matter of almost 24 hours, it suddenly expanded into a much larger object. And so in this particular case, it wasn't necessary to have a telescope to see this comet. It wasn't necessary to have the camera moving to track the sky. It only required a relatively short exposure, 30 seconds or so. So having a camera on a tripod, exposing for 30 seconds, the stars have hardly moved at all, and you can catch, for instance, interlopers like comets that come through the solar system. But there are definitely some targets that absolutely need you to be in the right place at the right time. In this case, it's a question of waiting for the comet, and everybody could see the comet as it came through and passed the Earth. But there are some other phenomena which you definitely have to be in the right place at the right time. For instance, aurora. So you notice we've gone back to slide film here. So again, this was quite a few years ago. This was more than 20 years ago. I had a trip to Iceland to see the aurora. Some of you might know that occasionally aurora are seen from England or from the UK. What you generally see is just the top of an auroral display. You have to go a little further north to the Arctic Circle, whether that be Iceland or Greenland or Lapland or Alaska, before you see the full glory of the northern lights. So you get these huge curtains of light which cover the entire sky when you get a nice auroral display. And this is just, again, a few minutes later, reminding you of how much things change in only a few minutes. For those of you who know your way around the sky, there's the constellation of Orion on the left side, there's the belt of Orion, and right in the middle is that little star cluster, the Seven Sisters, the Pleiades. So the auroral curtains, the auroral lights, are semi-transparent in that you can still see the stars in the background, but they are amazingly bright, and they glow with a wonderful green and red glow, depending on the time of night and the conditions. In this particular case, this is a wide-angle lens and a relatively long exposure, which means some of the subtle movements of the auroral curtains and the shimmering of the curtains, unfortunately, got blurred out. Now, I would love to go back to Iceland one day, maybe soon, and take a digital camera with me because they would be more sensitive and be able to take shorter exposures and perhaps catch some of this shimmering and some of this movement if you take a whole series of short exposures, which unfortunately has been blurred out somewhat in this old image taken with slide film. Another definite right time, right place. You have to be in the right time, place whenever you have a total eclipse of the sun. In this particular case, in 1999, friends and I went down to Cornwall and were disappointed not to see a total eclipse of the sun. So one came up 7 years later, and the track went through Africa, and it went through the middle of the Sahara Desert. And we figured it's not going to be cloudy in the middle of the Sahara Desert, unlike England. So we took an arranged trip. There was a group in the UK which basically shipped a whole load of astronomers out to the desert, plonked them down where you saw the eclipse of the sun. And again, because it only lasts a few minutes, and because in this case, a 300 millimeter lens, the sun doesn't move that much, it's perfectly okay to just slap the camera on a tripod. You don't need a telescope. You don't need to follow the stars because you're taking relatively short exposures, generally speaking, a fraction of a second, and therefore you don't need to worry about the movement of the Earth during these short exposures. And in this particular case, because the inner part of the corona, there's the disk of the moon covering the disk of the sun, so all you're seeing now is the atmosphere of the sun. The sun's atmosphere is very bright on the inner edge and gets fainter and fainter and fainter as you go out. And it's rather difficult to find one exposure that captures all of the information in the solar corona. So what you tend to have to do is take short exposures to get the detail on the inner edge and longer exposures to get the detail on the outer edge, and then you have to composite them together. So this is a composite of different exposures. For instance, a 4,000th of a second, a 1,000th of a second, 1/250, 1/25, 60th, 30th, etc. A whole load of exposures were taken to get different detail at the different brightness levels of the corona, and then they were all added together afterwards. And you can see the beautiful streamers that are coming out of the sun. You can see a sort of a north pole and a south pole, and lots of other extreme streamers coming out of the sun there. But unfortunately, you can only see the solar corona during a total eclipse, and you don't get total eclipses that often. If you want to catch one from England, you're going to have to wait quite a few decades before this happens back in the UK. Otherwise, you have to simply go wherever the eclipse is visible. It's been earlier this month, you may have seen news items of the eclipse that travel through Mexico, USA, Canada, etc. So let's have a think about, although you can do a certain amount with just a camera and a tripod, let's think about how you might want to go if you were interested in astronomy and you decided that you need a telescope. So what size telescope do you need to do astrophotography? Well, you can take it to the extreme if you like and say, right, that would be a great, I mean, wouldn't that be fantastic? It's now quite old, of course. You know, it was launched in 1990. So this telescope is 34 years old. It's going to appear on eBay before long because it's going to be decommissioned. Unfortunately, the buyer has to collect, though. That's the problem. But it's good for a little while. It's been going for 34 years, which is amazing for any scientific instrument, but it's not got that much life left in it. It is going to fail at some point. But of course, none of us can afford anything like that. It would be nice if we had a few $1 billion and could build one for ourselves, because we would then get fantastic images of distant galaxies or nebulae within our own Milky Way. But that's not really viable. What if we've got less than $10 billion? Well, if you've got less than $10 billion, you have a few options. One is another telescope that's been decommissioned. It costs about 100 million or so, but there's a telescope in the back of this 747. It's called SOFIA, the Stratospheric Observatory for Infrared Astronomy. They put a telescope in the back of the 747, and because infrared light tends to get absorbed by the atmosphere, you fly it as high as possible to get above as much of the atmosphere as possible. Hubble, of course, does that to extreme by going into orbit, but here a 747 goes as high as it can. This has been producing some wonderful images for quite a few years, but in the last few months it has been decommissioned. So again, if your pockets are deep enough, just watch out, because NASA are getting rid of this 747. What are other options? Well, If you've got a few million to spare, you can buy yourself a really big telescope and put it on top of a mountain somewhere. You don't have to buy one of these large telescopes because, for instance, the Liverpool telescope is the largest robotic telescope in the world, which means it works robotically. You don't have to go to the island of La Palma to use it. You can use it by sitting at home and basically using the internet and get some rather nice images of nebulae or galaxies. And indeed, although it's a research telescope, it is available to, for instance, schools as well as other educational sources to actually spend time on that instrument. So although researchers who put most of the money in get most of the time, it is also available for school kids to use throughout the UK and indeed throughout the world. So that is another possibility. But most amateurs wouldn't do that. They would say, if I'm an amateur astronomer and I'm interested in looking at the night sky, I want to buy myself a telescope. But unfortunately, it's really confusing as to which sort of telescope you might want to go for. There are lots of different types of telescope. They all look slightly different. They all have different prices, anything from a few £100 to literally tens of thousands of pounds. And it's not necessarily obvious at first sight why one of these telescopes is necessarily any better than any of the other telescopes. So there's a telescope which is quite common for amateurs. I'm not going to go into all of the details. Some astronomers delight in buying a telescope and then turning it into spaghetti by attaching a camera on the back. There's a camera on the back and a whole load of other things. And basically, for those that enjoy technology, they basically try and wire up as many things as they can and see if they can win the competition of how many miles of cables they can put onto a telescope. A lot of people aren't necessarily interested in that. They're only interested in, can I get nice images through my telescope? I look through the telescope, I see wonderful things. Can I obtain an image? Some people relish the idea of buying as much technology as possible and bolting it onto the back of a telescope and seeing what that produces. One thing to bear in mind when you're thinking about what type of telescope might I want if I'm interested in photographing the night sky, one thing to bear in mind is it's easy to assume that what matters is the telescope. But a lot of astrophotographers will tell you, well, it's actually not the telescope that matters. It's the mount on which you put that telescope. The telescope itself would just bolt onto this plate on the side. Because this mount is responsible for moving the telescope and tracking, following whatever object it is you're interested in imaging. And if you want long exposures, you've got to track accurately to make sure you can follow the objects accurately. And if you don't follow the object, it doesn't matter how good your telescope is. If you're not following the object, it's going to move. It's going to blur, just like the star trails we saw earlier. So you could argue that if you've got some money for a telescope and some money for the mount onto which to put the telescope, you really ought to invest as much money as you can afford in the mount. It sounds a little bit counterintuitive. You might think that you put all the money into the quality of the telescope you buy. But no, they say make sure that you're tracking as accurately as possible and then your telescope will deliver the sort of photos that you want. Perfectly sound advice, but that is a very massive, very precise mount for amateurs. Okay, it's for amateurs, but would you pay $10,000 for a mount like that, even before you thought about what telescope you're going to bolt onto it? It does get an exceedingly expensive hobby if you say, I want to buy a telescope and a mount to put it on. So the golden rule is don't jump into the idea of buying telescopes until you've thought about it or taken some advice from, for instance, an astronomical society. I've got a different talk, or I can give you advice if anybody is contemplating buying a telescope, either for themselves or for a young relative perhaps who said they want a telescope, then don't do it until you've thought about it. So as I say, I can certainly give you advice and I can point you towards a short talk I've given on how you go about thinking about the sort of telescope you might want to buy. If you did buy a telescope, where would you put it? Well, most people would like to have an observatory in their back garden. Now, okay, that's not a back garden. That's Mount Palomar in California. That's one of the largest telescopes in the world. It has a mirror that is 5 meters in diameter, so absolutely huge, roughly sort of the width of the front row here. I visited that back in the 1980s, I think it was. Yes, 1982. There's me looking a little bit younger. I might actually be wearing the same shirt. But yes, okay, that's me with slightly longer hair. Back in 1982, visiting this telescope and this dome in Palomar Mountain in California. When I looked at that telescope and that observatory, I thought, that is fantastic. When I buy a house, I'm going to buy a house big enough with a back garden big enough to have an observatory like that in, and then I'll have a really big telescope in it. Okay, it didn't quite work out that way. I had to downsize my ideas, and I went with a shed which I converted into an observatory. It's a shed, but it hasn't got a roof. It's got panels which lift up on hinges to expose the sky, and just to make sure the rain doesn't get in, I've got this sort of trailer cover, this tarpaulin over the top. So that was what I did in 1998. I had to downsize my ideas somewhat. Whoops, sorry. Inside the observatory, you can tell this is an old picture for two reasons. A, the observatory is clean, and it didn't take long for the spiders to invade. But secondly, you can tell this is an old picture because the laptop looks like an absolute brick compared to the thin laptops that we tend to get these days. But basically, that was how I did some of my astronomy in the early days, back in the, what was that, more than 20 years ago, more than 25 years ago now. But that sort of idea is great if you want to take pictures of the moon, for instance. So I've taken pictures of the moon through that telescope. You can get lovely detail, absolutely wonderful detail of the moon, and you can spend your time, oops, seem to be having a problem with the pointer here. The closest neighbor, our lovely moon, can be fascinating. You may think it's just the moon, but even if it's just the moon, just by observing all of the detail you can see, when the sun just catches these craters or these mountains, as the sun rises over some of these craters, you see things change. Not only day by day, but hour by hour, you can watch the sun rise over a particular set of craters and see how things change and see enormous amounts of detail in the edge of the moon there. But what I've described up till now has been extremely expensive. And I want to tell you a little bit about how you can keep the cost down. Yes, if you wish, you can spend tens of thousands on a telescope, you can spend tens of thousands on a mount, you can spend thousands of pounds on an observatory to put them in, and then you might have a chance of taking some interesting images of the night sky, some images of distant nebulae, distant galaxies. But you don't have to spend that much money. If you've already got a camera, then I would argue all you need is a tracker. And a tracker is just a device that will counteract the rotation of the Earth. If the Earth rotates once a day, well, strictly speaking, the Earth rotates once in 23 hours, 56 minutes. If that's how long it takes the Earth to rotate once, then if you want your camera to stay still relative to the stars, you simply have to rotate your camera one rev a day or once every 23 minutes, 56 seconds in the other direction, and then your camera will stay pointed at a particular distant star. Let's just remind ourselves, forgive me if this is stuff that you already know because you're a photographic society rather than an astronomical society necessarily. Let's just remind ourselves how imaging works. If we wanted to think about, do I want to buy myself a camera to do astrophotography? So with a monochromatic film or a monochromatic CCD chip in your digital camera, arguably all chips in digital cameras are monochromatic. They have no color sensitivity. But of course, if we wanted to take color images, how would we do that if we only had a black and white camera? We would do that by inserting colored filters, red, green, blue filters, take 3 images. That would give us a red, a green, and a blue image, which we could then combine either physically or these days in a computer to generate a color image. Of course, monochromatic film, black and white film, existed for quite a long time, as did color film. And color film is basically black and white film, but with the color filters embedded into the emulsion themselves. And the way that's done is subtly different between print film and slide film, but we're not going to worry about that. With digital imagery, then what we have is a monochromatic, sorry, it's doing the same again. Maybe it's just because it's probably just the case blocking the clicker here. With a color digital camera, it's still a monochromatic CCD chip. The chip doesn't have any color sensitivity, but colored filters are basically overlaid on the front of the chip in order to give you some color sensitivity. In other words, if you were to look in detail at what's going on in the chip, if we were to zoom into that area, we would see red filter, blue filter, etc., repeated over the entire surface of the chip. And so that means that what we would actually see then would be, we would pick up, you can see where the red pixels are, where the green pixels are, where the blue pixels are, then we would get red and green and blue information. Notice that we don't actually see them in the same place. The red pixel picks up what's hitting there, but the blue pixel picks up what's hitting in a slightly different place. So the computer has to reconstruct a color image from the red pixels, the green pixels, and the blue pixels. That's essentially how all digital color cameras work. If we wanted to buy ourselves a camera that's dedicated to taking astronomical images, rather than just say, I'm going to use the camera I've already got, well, you have a huge number to choose from. I've just shown a handful, a selection of 3 different cameras. I would imagine there's probably a couple of hundred different types of camera that you could, in principle, go with. For instance, a 2-megapixel color camera might cost you a couple of £100 or so. If you wanted more pixels, that will cost you more. And it might be surprising to learn that if you wanted a color camera, that might cost you, well, different prices, but let's just say for the sake of example, £2,000. If you wanted a mono camera, it costs you the same, which sounds a little bit odd, but the bottom line is, how much does it take to add that set of colored filters, the so-called Bayer grid, to the front of a chip? As far as a manufacturer is concerned, making a chip is expensive. Adding the colored filters on the top makes no difference whatsoever. So a lot of manufacturers will sell a mono camera and a color camera quite often at exactly the same price because it makes no difference to them. They might adjust the price depending on demand, but they won't adjust the price necessarily because it's more expensive to make a color camera, even though it sounds like it ought to be more expensive. If you're going to get a mono camera, but you still want to take color images, then you would buy a system to allow you to put colored filters in front of the camera. That, again, adds to the cost. Why would you choose to buy a mono camera and then choose to add filters? Well, it gives you an enormous amount of control. With a color camera, you have no choice but to take red, green, blue images all with the same exposure because the red, green, blue filters are part of the camera. But if you buy a mono camera, you have the choice of how you choose to put in colored filters. You don't have to put in red, green, blue colored filters. If your object that you're interested in photographing happens to be a cyan color, you can put a cyan filter in if you so wish. Or you can put in other filters that let through different wavelengths or different colors, if you wish, of light. So it gives you an enormous amount of control if you choose to do that, and some people do. But it starts to get very expensive. And what I want to talk about mainly this evening and show you examples of are what happens. Sorry, I'm doing it again. No, it's not you, sir. It's just that I have to look around the case, that's all. What if you've already got a camera? Now, I'm using a DSLR as an example just because I've got a DSLR. It would be applicable if you were talking about a bridge camera or a digital SLR camera or a mirrorless camera. It doesn't really matter. But I'm not, in general, talking about the tiny, tiny, tiny cameras that you get inside iPhones, for instance. But assuming people already have a camera of one kind or another that's got a reasonable sized sensor in it, a reasonable sized chip, then you don't have to think about, should I be buying a camera that's dedicated for astrophotography? I would argue, absolutely no, you don't have to. The camera you probably already own, I would argue, is very good for astrophotography. All you have to do is worry about the fact that the Earth is rotating. That's always the case. So you want to derotate the Earth. If the Earth rotates one way, you want to move your camera in the opposite sense to follow the stars. And how can you do that? You can build yourself a tracker. A tracker is just a device that turns the camera at 1 revolution a day to counteract the rotation of the Earth. I built one, I called it K2 for reasons I'm not going to go into. I built it quite a few years ago, and it's basically a few bits of aluminium, a motor at one end, a couple of AA batteries, a little potentiometer, and not much else. That's sort of all you need. That cost me about £20 to £25, depending on what bits and pieces you want to add to it. That doesn't include the gubbins on the top there. If you don't like the idea of building one yourself from scratch, you can just go out and buy yourself a star tracker. There are lots available. When I built this one, K2, very few star trackers were around and they were very expensive. These days there's lots of star trackers around and they're not quite so expensive. This particular one is called an Ioptron sky tracker. That's the one I chose to buy. You can buy star trackers for pretty much anything from 100, 200, 300 or more pounds, depending on how sophisticated you want them to be. But bear in mind, sophistication is a relative word, because what is a star tracker? It's a motor in a box. So how sophisticated do you want them? The only sophistication, there's obviously a worm wheel and a large worm gear there, obviously batteries, a little bit of electronics, a motor and a gearbox that makes sure this turns really slowly. Even though the motor is whizzing around at high speed, we of course want this big wheel, which is what the camera attaches to, we want that to turn roughly 1 revolution per day, so it's got to be geared down enormously. And the electronics here simply make sure that this turns at exactly the right speed so that this does 1 revolution in 23 hours, 56 minutes. So if you line it up correctly and make sure it's parallel with the Earth's axis, it will counteract the rotation of the Earth. So
So it would be a linear motor, not a stepper motor?
that particular one is probably a stepper motor. Mine, K2, was just a simple DC motor, but with these more sophisticated drives, they tend to be stepper motors. So having decided that's what you want, you basically set it up and bolt your camera to it. This little polar scope on the side here is basically a way of making sure that you're lined up with the Earth's axis. If the Earth is turning about a particular axis, you want to make sure you turn the camera in the opposite direction, but with a parallel axis. So you want that to be lined up to the North Pole. I'll show you that a little bit later. So that's just an easy way of doing it. A standard tripod thread here, a 1/4 inch or 3/8 inch, means that you can bolt on, for instance, a ball and socket joint or something like that, which allows you to point the camera in any direction you like, regardless of the fact that the sky tracker is lined up with the Earth's axis. Perhaps you can't see here, but basically you might use it with a wide-angle lens, you might use it with a portrait lens, you might use it with a little telephoto lens. It doesn't matter too much. You can't have an enormous lens on this simply because there is a weight limit to how much you can put on this before the whole thing falls over. So you might have a sort of a 3 or a 4 or a 5 kilogram limit to how much you can load these things on. But given DSLRs and modest sized lenses are not that heavy these days, that's generally not a problem. I actually chose to put a wide angle lens, and I also have tried it with a 300mm lens. So here's a Nikon with a 300mm lens on top of the sky tracker, the motor in a box. 300mm is about the longest focal length I've found that works well for astrophotography. It's the lens I use when I go on safari. Wildlife photography is another passion of mine, and a Nikon, in this case it's a Nikon 7500, is the DSLR I own at the moment. A 300mm f4 lens is the lens I use for taking photographs of lions and zebra and giraffe and all of the other animals in East Africa. I chose that lens partly because it's a nice focal length and partly because it's really small. It fits in the palm of your hand virtually, and it's very light because of the way it's designed. So it's not heavy and it's not particularly large, but 300mm is quite a good focal length for safaris, for taking pictures of lions without getting too close to them, and it's also, as it happens, great for astrophotography. So in other words, I found a lens which suits both of my passions, wildlife photography and astrophotography. One lens does me for both. I don't have to switch between the two. So this, I think, is a good place to break. I've had my half an hour, so I've given you the background, and in the second half, I'll show you some of the images I've taken with my Nikon and a sky tracker. Okay, let's break here. Okay, tea break over. So now we're going to have a look at a few images. I've given you the background of, in principle, how you can do astrophotography by spending tens of thousands of pounds, or you can get yourself a tracker which you can build for almost nothing, or you can buy for 100 or 200 or 300 pounds or something, and then you can use your camera on a star tracker. And that's what I'm going to show you for the remainder of this talk. The same camera I've been talking about up till now, it just happens to be the camera I'm using at the moment, a Nikon D7500, and you can take lovely images of objects out there in the universe. One thing you might notice immediately is beautiful colors. Unfortunately, our eyes don't work too well in color when the light levels start to drop. Perhaps you know how the human eyes are built. They're built with cones and rods. Rods work really well in low light, but don't give you any color discrimination. So when you look out on a moonlit night, you might be able to see where you're going, but you won't see colors, which is a real shame, because the colors are there. The colors are there, and cameras can capture them in many cases, even though you can barely make out the colors for yourself. So a camera on a star tracker will allow you to take pictures of nebulae or stars or galaxies, and those colors will come out. Now, I've already said that you can use a telescope, and I'm not trying to stop you doing that. If you're interested in buying a telescope and bolting a camera onto the back of it and taking astro images, fantastic. But bear in mind, it can be, yes, very rewarding, but to get the most out of astrophotography with a telescope will take you time, it will take you effort, and it will take cash. It is not cheap, and it takes time to master astrophotography through complex equipment such as a telescope on a big mount. You don't need to spend too much time figuring out how to take a picture when you're just slapping a camera on a star tracker. It's virtually switch it on, get the camera pointed towards the object of interest, and start snapping. So let's have a look at a few images that I'm talking about here. Before we look at specifics, let me just tell you that you don't necessarily have to go to the darkest skies in the world in order to get nice images of the universe. Here's an image. These are raw images rather than JPEGs because it's far better to take raw images if you're going to do a lot of astro processing. When I'm taking a picture of a lion, I don't care, I just take JPEGs, but when I'm taking astro images, I tend to take raw images. And on the left here is the picture you'd get effectively off the back of the camera if you just downloaded a raw image of a chunk of sky taken from relatively light polluted skies. In other words, lots of street lights around, producing quite a substantial glow in the sky. And although there is a nebula in there which is glowing away like crazy, it's rather difficult to see it. But with processing, you can bring out the detail. This is the same image processed in order to bring out the detail that you're interested in. In other words, light pollution from street lights has made the whole thing orange, but with the right software, in either software you write yourself or software that you get from somebody else. There's free software, and in some cases there's software you pay for, but there are plenty of examples of free software that will allow you to process astro images to pull out the detail that is, as it were, hidden inside those images. So don't be disappointed if you try taking a picture of the night sky and on the back of the camera you see that and you think, my gosh, that looks horrible. No, don't worry about it. Once you've got it into your computer and have started processing it, you can get rid of that glow. As long as the glow isn't too bad, as long as the light pollution is reasonably moderate, you can use software to mitigate the effects of light pollution. You could also use filters. I'll come to that in just a second. So let's have a look at one or two examples of what we can do. So here, again, I'm showing you what I'm taking at the bottom there. So the same camera, a 300mm lens, a whole series of short exposures. Remember, very rarely do I ever take a long exposure. A whole set of short exposures works for a lot of reasons. If a plane happens to go by, I can just ignore that particular frame, that particular exposure, and add up all of the others. If clouds happen to come scudding in and ruin a couple of images, doesn't matter, all the others will be fine. If you take one long exposure, it can be spoiled by a satellite or an aircraft or something else crossing your line of vision. But if you take lots of short exposures, you can just filter them later and say, I'm going to keep that one, chuck that one, chuck that one, keep this one, keep this one, keep this one, and then add up all the good ones. So nearly always I take a large number of short exposures, not a small number of long exposures. This is a nebula. For those who know the night sky, it's sort of just to the left of the constellation of Orion. It's called the Rosette Nebula. It's where stars are being born. And although you might think of objects in the universe as being far, far away, why else do we need telescopes if they're relatively close? This is a relatively nearby nebula. And by nearby, I mean in terms of how large does it appear in the sky, well, that appears larger than the full moon. Its diameter is roughly 3 times the size of the full moon. Not size in actual size, but size as it appears in the sky. Remember, the full moon can be covered easily by just holding your thumb up to the moon. This is larger than the moon, so you don't need a fantastic telescope with a huge focal length in order to zoom into the sort of detail that you can see in this particular stellar nursery. And by stellar nursery, I mean all the stars in the center of this nebula are relatively young. This is where stars are being born. Stars are born when you start with a lot of hydrogen, it collapses under gravity, and then stars are born in the center. At the other end of star existence is star death, and this particular star blew up a long time ago. You might notice the stars are a lot blobbier in this because it's a very old picture. This is 20-something years old, this particular image, so it's not one of my best, but I like to show it because it again shows this particular nebula, this particular so-called planetary nebula, nothing to do with planets. This means a star has come to the end of its life and the outer part of the star has been blown off into space. So the outer atmosphere of the star has now produced this nebula, this blue and rather orangey nebula. This is what our sun is going to do. In a few billion years, our sun will look like that. The sun will expand and blow off all of the outer part of the atmosphere and leave a little small star in the center. I'm showing this one not because it's a fantastic image, but I thought it was quite curious that you can photograph objects in the sky and you can say, well, does Hubble do a better job? So that's the Hubble Space Telescope. And yes, the Hubble Space Telescope does do a better job. I will be the first to admit that. But remember that my picture was taken on a tracker that was sort of, 20 odd quid. The Hubble Space Telescope cost $10 billion. So yes, it's a better image. Is it a billion times better? I would say not. There's an enormous amount of satisfaction to be gained by taking objects that Hubble or the James Webb Space Telescope have imaged and saying, can I see them as well? You're not going to get images that are anywhere near as good, but it's still fun to say, I've taken a picture of the same object that the Hubble Space Telescope has imaged some years ago. This is a star, again, one that's coming to the end of its life. This star is still living in the sense it hasn't died yet, but there's a star right in the middle of this nebula, which for hundreds, if not thousands of years, has been, again, losing material, which is drifting off away from the star and producing this huge pink nebula. Pink is not that uncommon for the pictures that you take of gas clouds out in the universe, because most of the gas in the universe is hydrogen, and hydrogen glows pink at the red end of the spectrum when it gets excited. So it's not surprising to find a lot of nebulae all seem to have a sort of pinkish glow to them. Quite often a little bit of blue as well. Blue indicates oxygen, red indicates hydrogen. We can tell what it's made of just by looking at its colors. That's the power of spectroscopy. So this was quite a nice nebula to photograph. Partly because there's other interesting things in the background, like these large collection of blue stars here, but also notice the focal length that was used. This is not a long focal length lens. This is an 85 millimeter lens. It's basically a portrait lens, and yet you can get that sort of detail because, again, this is such a huge object. It's quite a few light years across, and it's quite a few light years away, but in terms of how big does it look in the sky, it looks bigger than the diameter of the full moon. So you don't need enormously long focal lengths in order to catch objects with quite a nice amount of detail in them. This is the one example where I've actually used a filter. Up till now, I've said I'm just taking images with the camera, and the colors that you can see are essentially natural colors. This is the first time I've actually used a filter. And this picture of a star that blew itself to pieces about 10,000 years ago, in other words, there was a star somewhere in the middle there, and it's blown itself to pieces, and these little strands here are the bits that are left. It's basically a large bubble of gas, and it's been expanding for the last 10,000 years or so. So these are the sort of edges of the bubble, if you like. So this is the result of a supernova. A star died, a very massive star died, very violent death, and threw all of the material out at a fair fraction of the speed of light, and that's how it looks some 10,000 or so years later. This picture was taken outside my front door. And outside my front door, there's a whole load of streetlights. I live in a sort of suburban area. So this was taken very close, perhaps less than 10 meters away from an LED streetlight, which was sending loads of light down onto my drive in front of my house. But the advantage of using a filter, the tri-band, simply means that it lets through 3 specific wavelengths of light. Those wavelengths of light have been chosen to let through the red and the blue here. You can see the red tinge and the blue tinge. The red tinge is because it's made somewhat of hydrogen, and the blue tinge because a fair bit of it is made of oxygen. Oxygen and hydrogen emit light at very specific colors, very specific energies, very specific wavelengths. So if you get a filter that only lets those wavelengths through, you can see the nebula very clearly, but all of the light from the LED street light, most of that doesn't get through the filter, because most of that light is not at these specific colors. Most of the light from an LED is spread over the entire spectrum. So you can mitigate the effect of LED streetlights if you use one of these filters. And again, I haven't got time to tell you all the detail. If anybody wants to have a go, I can give you details. I can send a link to Malcolm to distribute amongst you, telling you what sort of filters are good for this sort of photography or that sort of photography. I've also got a short talk that describes it. I'll send you the link to that as well. So even under very light polluted skies, you can still take pictures, for instance, of a supernova remnant, some star that exploded 10,000 years ago. Again, this is a 300mm lens. Again, this supernova remnant is much larger in the sky than appears the full moon, for instance. This is something like 3 degrees across, 6 times as large as the diameter of the full moon. What other objects have we got here? Well, again, this is now unfiltered. This is, again, we've done with filters, so this is just straight. The universe is very colorful. So little bit of pinks down here and pinks up there is because these are made of hydrogen. A lot of yellow in the middle because there's a very yellowish star here. It's actually a little bit redder and the color isn't perfect. And that is illuminating this cloud of gas and reflecting off it, producing this yellow glow. Again, there's a cloud over here, and embedded in that cloud is a very blue star, and that blue star light is reflecting off this nebula, producing the blue glow down here. So all of these colors are as close as I could get to the sort of colors that you would expect to see if your eyes were sensitive enough to show you those colors. The colors are real. This is not like a Hubble image where they've deliberately changed the colors to try and reveal certain structures within the image. This is what it actually looks like. That is genuinely pink, that is genuinely yellowish or orangey, and that is genuinely bluish. And it's sometimes surprising to realize just how much color there is in the night sky. And just as a point of reference, if you're interested in looking up on a star atlas where it is we're looking, this is the star Antares, the brightest star in the constellation of the Scorpion. That's a star cluster comprising hundreds of thousands of stars packed into a very small area. That star is called Rho Ophiuchi, which gives its name to this whole area. There's a huge cloud of, as you can see, gas that's lit up by different stars, and notice that there are some dark areas as well. Notice that there are very few stars visible through these dark clouds. There's a lot more stars visible outside these areas, so these are dark clouds which are obscuring the light from more distant stars. So we can learn an awful lot about what's going on by looking at the structure and looking at the colors. Again, notice this is not a particularly long focal length, a 135mm lens in this particular case. 300mm lens, lovely image of the Andromeda Galaxy, one of our neighbors. The Milky Way galaxy in which we live looks somewhat similar to that. If we could travel to the Andromeda Galaxy and look back at the Milky Way, it would probably look very much like that. A huge spiral galaxy. Again, 300mm tells you that this thing is absolutely huge in the sky. It is much bigger than the full moon. You don't need a very powerful telescope to see it. You can just about see it with the naked eye on a nice, clear, dark night. But with a camera and a longish exposure, this was an exposure of a total of 30 minutes, you can see an enormous amount of detail in terms of the spiral arms of the galaxy. You also notice a couple of other fuzzy blobs. These are clearly not stars because they're way too fuzzy. These are a couple of small galaxies that are basically satellites of the Andromeda galaxy itself. And some of my friends in other astronomical societies spend their time watching what the stars are doing in the Andromeda galaxy, seeing if they can see any particular star that suddenly brightens. Either if it's really bright, it might be a supernova going off. If it's not so bright, maybe it's a nova, a star that suddenly gets brighter and then decays away. By looking at these stars, you can effectively calibrate, in a sense, the distance to the Andromeda galaxy. This particular galaxy is 2.5 million light years away. So the light has taken 2.5 million years to get from the galaxy into the camera. So it's just as well I opened the shutter when I did to catch the light that's been traveling for the last 2.5 million years. There's my tracker again. But the picture in the background, I'm now going to show you what is probably the least impressive image you have ever seen in your life. And I'd be surprised if you don't agree with me once you see the final image. Who can forget 2020? Lockdown. Remember all of those little footprints that appeared on the ground in supermarkets and on pavements? Everybody was looking down at their feet, being told, keep 2 meters away from everybody else because of COVID. But Stephen Hawking said, remember to look up at the stars, not down at your feet. So during the lockdown, I couldn't go to the pub and drink with my friends, so I thought, let me see if I can take a picture of the most distant object I can catch without a telescope. With my camera on a tracker to make sure they don't blur, what is the most distant object I can hope to catch with my camera? A camera that's built for daylight, but I'm going to try and catch an object from the other side of the universe. So I looked up in a research paper a very bright galaxy, bright in the sense that it produces a lot of energy, but a very distant galaxy. We'll come to the distance in just a second. And I looked up where it would be, and I would expect it to be there. I pointed the camera where I expect this particular very distant galaxy to be. It happens to be next door to that star. That star is bright enough that I can easily see it through the viewfinder of the camera. I can easily focus on it to make sure everything is perfectly in focus. So I'm hoping that the galaxy that I'm interested in is in a little square there. So I took a long-ish exposure, about 2 hours. This is taken in the summer of 2020. As you know, you don't have much dark skies in the middle of summer from England. You only have a couple of hours between the end of twilight in the evening and the start of twilight in the morning. So 2 hours was about the longest exposure I could take. So I then zoomed in with my 300mm lens on the tracker. I zoomed into a little square just to the top right of that star. And, oops, that's where I was looking. And I expected the center of that square to hold the galaxy that I was interested in. So I zoomed in, and that in the middle there, as indicated by the 2 red lines, that is the galaxy I was trying to catch. And if you bothered to blow it up, it doesn't look any more than 1 pixel in the image. But it is only 1 pixel, which that's one of the reasons I had to make sure it was quite well focused, because virtually all of the light from the lens is going into just 1 pixel in the image. But the distance to this object is absolutely phenomenal. There it is blown up. It is basically 1 pixel. Maybe some of the surrounding pixels have caught some of the light as well, but essentially 1 pixel out of the 20 million pixels in the sensor, that's the only pixel that matters. But the distance to this object is truly mind-boggling. How long has the light been traveling in order to get from this distant galaxy to the camera? It has been traveling for 12.4 billion years. That is most of the lifetime of the universe. The light left this object very, very early on after the Big Bang, and it's been traveling for 12 billion years. The light was traveling for 8 billion years even before the Earth existed, and then it traveled on for another 4 billion years after that. This object is so far away, the universe we know is expanding. We can tell it's expanding from lots of different measurements. And this object is so far away, the galaxy is actually receding from us at twice the speed of light. And yet, it is still possible for the light eventually to reach us. So the light's been traveling for 90% of the age of the universe. It's traveling away from us at twice the speed of light, and the distance to that galaxy now is 24 billion, not 24 million, 24 billion light years. That is an absolute phenomenal distance, and it's been captured by a camera without a telescope. It's just captured with a camera and a telephoto lens. So kudos to Stephen Hawking to make me think, let's not look down at our feet, let's look up at the sky and just imagine how far we can see into the distant universe. And although it is the least impressive picture in terms of aesthetics, it's just a pixel. In terms of what it stands for, I think it's one of the most amazing pictures I've taken. Forget all of the other nice galaxies and nebula. I think that one pixel is in itself amazing. So let me finish just by saying a little bit about how you can make the most of dark skies. Yes, if you're under light polluted skies, you can get away with using filters, but it's so much better if you can go to dark skies and actually see for yourself just how wonderful the sky can be. So my friends and I realized some time ago that we have common interests. We were all interested in wildlife, we're all interested in astronomy, and we're all interested in photography. So wildlife and astronomy come together. If you use a pair of binoculars, you can use it for both. Wildlife photography, of course, you see wildlife and you can photograph it, and we are talking about astrophotography. So all of these three come together if you visit Africa and go on safari. You can basically look and photograph animals by day. You can look and photograph the sky at night. Sleep when you get home. It's a waste to go on holiday and not actually make the most of the day and make the most of the night. So that's what some friends and I have done a few times. We can't afford to go to Africa every year. It's too damn expensive. But we go on safari whenever we can. And I always take a tracker with me. There's that polar scope, which again, remember, you line up on the North Pole. That's what you actually see. An app tells you if you are, it knows, the app, of course, on your phone, knows where you are from GPS. It knows the time from GPS. And so it can tell you if you're at this point on the Earth and this is the time, then when you look, this is where Polaris ought to be. Not quite at the North Pole. Polaris ought to be at the sort of 8:30 o'clock. At this particular point, that's where Polaris ought to be. So you can just move your tracker until that's where Polaris actually appears in your polar scope. This is the reticle, if you like, that you see through that polar scope. Yes, you're looking with your eye this way. This is the direction of the North Pole. You're looking through this end, and that's what you see. So you simply adjust your tracker until Polaris is in the right position. Bam, you are then parallel with the Earth's axis. However, that is really trivial in the UK because you can see Polaris. But if you go to East Africa, remember the Earth's axis is pointing to the North Pole. The Earth's axis is pointing to the North Celestial Pole. So from England, you can easily work out where Polaris is. But if you go to East Africa, where is Polaris? It's on your northern horizon, hidden behind elephants or mountains or something else. And the same is true for the South Pole. If you look in the other direction, the South Pole is on your horizon as well. If you're close to the equator, you can't see either pole. So that's a bit of a problem going to Kenya, which is one of my favorite countries to visit. The equator runs right through the middle of Kenya. So if you go to Kenya, you can't see the North Pole and you can't see the South Pole. So you have to come up with more creative ways of making sure that your tracker is aligned. I'm not going to go into a huge amount of detail, but there are ways you can do it. You can sort of figure out which way's north by using a compass. It's not quite so accurate, but it gets you in the right ballpark. And you can still take images of interesting objects when you're on the equator. There's one of our satellite galaxies. Remember we said a moment ago, there's the Andromeda galaxy. It's got a couple of small galaxies buzzing around it. This is one of the small galaxies that's buzzing around us. This is a so-called Magellanic Cloud. It's a small satellite galaxy of the Milky Way. As far as we can tell, it's sort of orbiting around us. Again, notice it didn't need a very long focal length. 85 millimeters was all that's required. In terms of the Milky Way, it's amazing how bright the Milky Way is. And it's difficult to show you how bright the Milky Way is because we're just projecting images on a screen. But just to give you a taste of what it's like, if you imagine this is what you would see of the Milky Way as seen from England, you would definitely see the Milky Way stretching across the sky, and you would be able to see structure within the Milky Way, dark areas of dust and brighter areas. But when you go to somewhere like East Africa, what you actually see is something more akin to that. You can see a huge amount of detail just with the naked eye by looking up at the sweep of the Milky Way. It's not just a fuzzy band across the sky. You can see all sorts of detail. And of course, if you photograph the Milky Way, although you don't see color by eye, as soon as you photograph the Milky Way, you can start to bring out a little bit of color in there. So some stars look a bit more red, some stars look a bit more blue. That, by the way, that bright thing there is the planet Jupiter. That bright spot there is the planet Saturn. This was taken quite a few years ago from Safari. Notice, again, this is not in any way a long focal length. On quite the contrary, this is a wide-angle lens, 35 millimeter, and you notice from the rectangles here, this is a mosaic of different images because we're talking about a large chunk of sky. So we want a wide-angle lens, and even then we didn't get everything in that we wanted. I could have mosaicked even further and followed the Milky Way right across the sky. It's a question of how many hours you want to spend imaging. In this particular case, you can see that's something like a 20-minute exposure for each of the frames here. In terms of what we're actually looking at, remember there's a huge number of stars. I'm not sure how many stars have actually been caught in an image like this, but there's far more stars than you can see with the naked eye, because as soon as you take long exposures, you start to see fainter and fainter stars. And because there are so many stars in the background, it's now actually quite difficult to see the constellations because the bright stars are almost lost against this background of fainter stars. If we compare with a much earlier picture I took with slide film many, many years earlier, we can sort of see the, for some people, familiar S shape of the constellation of Scorpius. This is one of the few constellations that looks a little bit like the animal it's supposed to represent. Claws of the scorpion, the body of the scorpion, and a sting in the tail right at the end there. But it's difficult to see where the hell is Scorpius in that image. It is there. We can actually join the dots, and Scorpius is indeed there, but those bright stars are almost lost because there are so many faint stars. You forget just how many stars there are out there. You might, by your naked eye, only see a few thousand, but as soon as you start imaging, you realize there are tens of thousands of stars that can easily be imaged in relatively short exposures. If we just zoom in a little bit into the center of that particular image, again, and we start identifying what's there, not only can you simply take a wide-angle chunk of the sky and say, well, there's the Milky Way, and there's a recognizable star. If you wish, you can actually start saying, apart from there's Jupiter and there's Saturn, which I mentioned before, you can start to say, well, there's some interesting star clusters and nebula. There's M16, the pillars of creation. There's M17, the swan. There's M80. What do I mean by M? Messier identified all of these clusters and nebulae back in the 18th century. He looked at these objects and started numbering them and labeling them, and we can actually apply those numbers and labels. That's not by any means all of the interesting objects in the picture. That's just a tiny number of the interesting objects that might be caught in a wide-angle view of the sky. You might look at that and say, well, all of the interesting objects seem to sort of, I don't know, they seem to stop there. Does that mean there's no interesting objects further south? No, it means Messier was a Frenchman, and he did all his observations from France, and he couldn't see any further south from France. So his view, if you like, from the south of France stopped there. The horizon stopped him seeing any further south. So there are all sorts of interesting objects further down. They just don't have the so-called Messier numbers because he never catalogued them. But there are huge numbers of interesting objects out there, and if you wish, you can zoom in on detail. Or, of course, you might decide, well, is it worth switching to a telephoto lens and looking in a little more detail? For instance, there's a very interesting pair of nebulae there called the Lagoon Nebula and the Trifid Nebula, and I wondered, well, I've just taken a whole load of wide-angle lenses. Before I pack up for the night, is it worth just switching to the 300mm lens and seeing if it's worth putting the 300 on the tracker and getting a little more detail? So I did that, and yes, you can see more detail. This is the same rectangle here. Lots of detail in this nebula. It looks rather pink because it's mainly made of hydrogen. This one is a little different. It's pink, and perhaps you notice a bit of blue there. Pink because of hydrogen, blue because a blue star is lighting up some of that nebula. And it's pushing my luck somewhat, but you could, in principle, take a tiny bit of that image and say, Does it blow up? Well, it doesn't blow up particularly well, but you still can see detail in this nebula. You can definitely see the colors of the pink and the blue, and you can see some structure. This nebula definitely has structure. So you could argue, well, yes, it's sort of worth taking a telephoto lens of some of the detail that's visible in the wide-angle lens of the Milky Way. But I would argue that if you're going to go anywhere in the world that gets away from light pollution, doesn't matter if it's Africa or the middle of nowhere, anywhere, whether it's the middle of the United States, the middle of Asia, South America, Africa, whatever. If you're going to go anywhere where you've got a chance of getting away from street lights, pack a star tracker with you. It doesn't add more than, I don't know, about 1 kilogram or so to your luggage. If you've got a 20 kilogram luggage allowance, why not make room for 1 kilogram of photographic gear? And then when you get away from light pollution, you can bang your camera on your tracker and you can take wonderful images of the universe. Thank you for listening.